Hi everyone. Today I want to talk about intermolecular forces. I'm going to be using the PowerPoint presentation that I presented in class. So if you have a copy of that, go ahead and take that out and follow along as we talk intermolecular forces. All right, so intermolecular forces are really important because without them, we wouldn't have the ability to have anything in the liquid state. We wouldn't have the ability to have anything in the solid state. Everything would be gases, just kind of buzzing all around. So intermolecular forces are the forces that allow us to have different states of matter. Okay. So as I move through here, I'm going to skip this part on the molecular comparison of gases, liquids, and solids because I think we've talked about that enough in the past, and you can read through that if you need to. But I would like you to remember that the state a substance is in at a particular temperature depends on kinetic energy, okay, and also the strength of the attraction between the particles, which is what we call the intermolecular forces. All right. A quick just breakdown of these two words. So we have something called intramolecular bonds and then intermolecular attractions or forces. So an intramolecular bond in this picture that we look at right here, okay, an intermolecular bond is the bond that holds two elements together in either a molecule or a compound. Okay, so this bond between the hydrogen and the chlorine in this hydrochloric acid is an intramolecular bond. Intramolecular bonds are either ionic, covalent, or metallic. And that's not what we're addressing today. So what we are talking about is between molecules. So here is a molecule of hydrochloric acid. Here is one as well. Between those molecules, we have something called an intermolecular force, or sometimes we refer to it as an IMF. These are called forces or they are called attractions because they are certainly not as strong as a bond, but they're strong enough to hold molecules together and allows us to have different states of matter. All right, I think this slide is just a reiteration of what I just said, so let's move on beyond that a little bit. Something interesting about intermolecular forces, again, it is the forces between molecules, is that it is going to control the properties of liquids such as boiling point, melting point, vapor pressure, viscosity, surface tension, volatility. So it helps us have all of these distinguishing features of liquids that we kind of know about, and all of those are dependent upon the strength of the intermolecular force that's present. As a whole, there are several types of intermolecular forces. As a whole, we refer to them as what are called van der Waal forces. So if you hear someone talking about IMFs or intermolecular forces or van der Waal forces, they are talking about the same thing. Okay, here is the list of van der Waal forces that we will cover. So the first one being ion dipole, then hydrogen bonding, dipole-dipole, and London dispersion forces. Okay, these are all the van der Waal forces or the IMFs that we're going to talk about. We're also going to learn how to figure out which molecule might have which particular IMF. All right, so let's start with the first one. This is an ion-dipole interaction. Okay, so it is the interaction between an ion and a dipole. These are important when we're talking solutions of ions. Okay, so this is what we're talking about when we're talking about ions that are soluble. The strength of these forces are what make it possible for ionic substances to dissolve in polar solvents like water, for example. So why does sodium chloride maybe dissolve in water? This has to do with the ion-dipole intermolecular force. All right, so here is how this works. An ion-dipole interaction, when we put ionic compounds that are soluble in water. And remember, you can tell if something is soluble by looking at your solubility table. Okay, so the table that we use for double replacement reactions, the solubility table, you could look at that to determine if something was soluble. When we put something that's soluble in water, like for example, this magnesium chloride, what happens is the magnesium chloride compound dissociates or breaks apart. That word means break apart. It breaks apart into its ions. So Mg has a 2+ charge, chlorine a 1- charge. When we put magnesium chloride into water, it will break apart into its ions. And remember, ions are charged particles. Okay, so in the ion dipole interaction, the ion portion of that would be the ions that dissociate from the soluble salt. Okay. Water then is a polar molecule. So if you think about, I'll just like quickly draw a little Lewis structure for water. Oh, there's my hydrogen bond. Here are my lone pairs on water. Water is quite polar. Okay, so this end of the molecule where the oxygen is slightly negative, and this end being partially positive, as well as right here, partially positive. Okay, so here is our polar water. Now, what ends up happening is the negative parts of the water will attract to the positive ion that has dissociated, and the positive parts of the water will attract to the negative ion. Here's a picture down here. I used magnesium chloride in this example, but this picture is actually of sodium chloride. Okay, so when we have, oops, that's not a pencil. When we have NaCl, okay, this will dissociate into water, into sodium ions. That's a positive charge, and chlorine ions, negative charge. And this is essentially how the ion dipole interaction looks. So here is our positive sodium, and it is attracting to all of the negative portions of water. Okay, these are all little water molecules here. They look a lot like mine up here, right? With the lone pairs making this end partially negative and these ends partially positive. And then the opposite will happen with the chlorine ion, right? So here's our chlorine ion right here, and all of the positive portions of water, I don't know why I just pointed there, here, are attracting to the negative portion of the chlorine. Okay. Now, when this particular type of interaction occurs, it is very strong. This is actually the strongest intermolecular force. Okay, so of all of the ones that were on a couple slides ago that we're going to talk about, this one is definitely the strongest. So an ion dipole interaction is the interaction between ions that dissociate when something soluble is put into water, and then our water molecules attract to the different various parts of the ion depending upon charge. Okay. All right. The next IMF that we want to talk about is something called a dipole-dipole interaction. This is quite similar to what we just discussed. Okay, so if we have a polar molecule, so now I need you to think back a little bit. Think about your Lewis dot structures that you draw, and think about when you have a molecule that you claim to be polar. Let me just draw one quickly for you. So what if we have like, oops, pencil. I wonder how many times a day on my videos I do that. If you've watched any of my other videos, I do that all the time. Oops, there's my little bond. Okay, and then this guy has some lone pairs right here. That is a terrible drawing. My goodness. Let's try that one more time. All right, so here is our P. Okay, this particular molecule, pH3, is polar. We know it's polar. We've got a pair of lone pairs here. And so this is making our molecule overall polar. When we have a polar molecule like this, we end up having dipoles. And so what we know about this particular molecule is that this end of the molecule is partially negative. Okay, and this end of the molecule here, here, and here is partially positive. Now, This one was easy to figure out because there is some lone pairs here. We know that's going to be the negative sort of end of our molecule. But if that wasn't there or you weren't certain, you could always do the subtraction between the electronegativity of phosphorus and hydrogen. Subtract those, see where that, so this is bond polarity, see where the polarity of that bond falls on our little spectrum of nonpolar, polar, or ionic to figure out what's partially positive, what's partially negative. Okay. These are called dipoles. So when we have something that's partially negative and partially positive, we have created what's called a permanent dipole. This happens in all polar molecules. And these dipoles are attracted to other molecules just like what we saw here. So this was an attraction between positives and negatives, and we would see a similar thing here. So if we had another molecule, and of course I didn't leave myself much space to draw this. Let's see if I can kind of get this in here. Let me erase some of my, let's erase this. Okay, and I'm drawing this very oddly because I did not leave myself much room, but you'll get the gist. Okay, so perhaps, and I'm wondering, can I change my color? Yeah, I can. We've got some of this negative part, this P, oh goodness, attracting to the positive part of this molecule. Now, horrible diagrams aside, what you need to take home from this is in a dipole-dipole interaction, the positive part of a molecule is attracted to the negative part of another molecule and vice versa. Okay, so positive ends attract to negative ends and vice versa. This is a dipole-dipole interaction. Let's see what we say here. So the positive end of one attracts the negative end of the other and vice versa. And, this is just kind of an important point here. These forces are only important when molecules are close to each other. This interaction has to happen in fairly close proximity in order for these attractions to sort of take place. Okay? All right. Now, in this grand scheme of things, dipole-dipole interactions are not as strong as ion-dipole interactions. They are quite strong, but not as strong as ion-dipole. Okay? All right. And one way to tell like which dipole would be stronger than another dipole is to just look at the polarity difference. Okay, so the strength of that dipole is going to help you determine which would have a stronger IMF than another molecule that also has dipole interactions. Okay. I'm going to come back to this one because I want to talk about hydrogen bonds first. I'm skipping all this, but I will come back. All right, another type of dipole interaction is called a hydrogen bond. It is still an IMF. So let's go back to our pencil here. I'm just going to, in brackets, put IMF. It's still an intermolecular force. It is not an actual bond. However, it is such a strong intermolecular force that it rivals the strength of a bond. Like, it's close. It's definitely not as strong as a bond, but it's a really strong intermolecular force. And so we give it this name of hydrogen bonding. Now, bonding is a little bit of a misnomer because this is not a true bond. It is still an intermolecular force, but it is quite strong. Now, it's similar to an ion dipole. It's similar to a dipole in that we've got negative ends attracting to positive ends, but we have a specific interaction going on here. So in hydrogen bonding, this is specifically when hydrogen is bonded to either nitrogen, oxygen, or fluorine. That is it. So way back on our dipole page, I think I did... what did I do? A phosphorus and hydrogen, so phosphorus trihydride. That would not be hydrogen bonding. It is dipole because it's polar, but it would not be hydrogen bonding because it is not hydrogen bonded to O, N, or F. All right, when hydrogen is bonded to O, N, or F, it is an unusually strong dipole interaction. And it has to do in part with the very large electronegativity difference between hydrogen, nitrogen, oxygen, or fluorine. Okay, hydrogen being 2.1 Paulings and fluorine all the way up to 4 Paulings. So the difference in electronegativities between these elements is really large, which creates a really strong dipole. Okay, and so again, positive ends attracting to negative ends, like for example, right here. Okay, so in this bond right here, hydrogen would be the partially positive side of this molecule, oxygen being the partially negative. And then over here, this is partially negative, this is partially positive. So we see this interaction between the partially positive part and the partially negative part. They are attracted to one another. And the same thing happens when it is H bonded to N. Oh, I don't have any H bonded to F, but that would also be the same. Okay. Now, hydrogen bonding is kind of a cool phenomenon, and it leads to some pretty special stuff, especially in water. So if we look at a water molecule, right, just drawn very quickly here with our lone pairs, this is hydrogen bonding, right? So we have the partially negative end of our water, the partially positive end over here, okay? And this is H bonded to oxygen. And so this dipole that forms here is a hydrogen bond. And this is what gives water some of its really, really unique and interesting properties. All right, so let's see what we have here. I think this is everything I've covered, just checking. Good. Oh, this at the bottom is just talking about how when we have hydrogen bonded to one of these very electronegative elements, like fluorine, for example, or oxygen, the pull on electrons is so hard that the hydrogen's nucleus is exposed. Those electrons are pulling, the electrons from fluorine are pulling so hard on hydrogen that it is actually exposing its nucleus. So just kind of a fun little fact there. Another fun fact is hydrogen bonding accounts for why liquid water is more dense than solid water. Now, this is unusual in the liquid world. Typically, it is the opposite of this. However, if you think about a glass of water with an ice cube, okay, the liquid form of that water is more dense. We know this because the ice is floating in the liquid water. Now, if you did this with other liquids, this would not be the case. All right, so hydrogen bonding is responsible for the fact that solid water is less dense than liquid. So this says in liquid water, hydrogen bonds are constantly broken and reformed as the molecules slide past one another. Remember, in a liquid, those molecules are in constant motion and they are sliding past one another. It's called translational motion. And that is causing the hydrogen bonds to break and reform and break and reform. But in solid water, they don't slide past one another. In fact, they just sit there and vibrate, vibrational motion. There's far less freedom for them to move. And because of this, the hydrogen bonds force the molecules to spread out. And so this is why, we've got this little phenomenon here. This person evidently froze this water bottle. Okay, and you can see the solid water expanded up and out of this bottle. Perhaps you have experienced this on your own. I know I have. I accidentally put a like a bubbly water, like a sparkling water in my freezer in my school fridge at work just to cool it down really quickly, but I forgot about it. And it blew up. The can blew up. It blew the door off my refrigerator, and it was terrifying. But this is why this happened. So that bubbly water composed of obviously water, and it froze, and it was bound by the constraints of that can, and it blew the bottom of the can totally off. So yeah, kind of a powerful thing we're talking about here. All right. Oh, I need to go back. Okay. So, and by the way, just in our kind of continuum of IMF strength, so ion dipole, still the strongest, but directly below that would be hydrogen bonding, and then directly below that would be dipole-dipole. So I'll go over this again, but that's sort of the strength of IMFs. Now let's talk about the least the least strong IMF. Is that a sentence? The least strong IMF? I don't know. Here we go. We're going to talk about it. It is called a London dispersion force. Okay, and this happens only with non-polar molecules. All right, so think about nonpolar molecules. Like here we go, let's do just CO2. Okay, so here is our CO2 molecule. We've got some, oops, nope, ignore me. There we go. Oh, I knew that was going to happen. There, we'll just draw it correctly. Okay, here is our CO2 molecule. This is a non-polar molecule. We've got symmetry here. The oxygen is pulling on the carbon in this direction, but this one is as well. So those dipole arrows cancel out, and overall we have a non-polar molecule. Now, obviously, the London dispersion forces that happen with nonpolar molecules aren't going to be as strong because they don't have that permanent dipole, that permanent magnet, essentially, that's giving this IMF strength. But they do have some strength, and we know this because we can get nonpolar substances that are solids, like wax, for example, or oil. If you put oil into your refrigerator and cool it, it will solidify. But it doesn't take much to get it back into a liquid, right? You take that oil out, you put it on your counter even, depending on how warm your house is, and it certainly will turn back into the liquid stage. If you've ever melted wax, it doesn't take much energy to turn solid wax into liquid wax. That's because both wax and oil are non-polar molecules, and the only intermolecular force at play here is a London dispersion force, and it's just not super strong. Okay, so here is how this works with London dispersion forces. It's actually so interesting. So in a London dispersion force, we end up getting a very temporary dipole. Let me explain how this happens. Okay, so I'll just read this statement, then I'll kind of explain what it says. So it says, while normally the electrons in the orbital of helium would repel each other, we know that electrons repel each other. They're unfriendly with one another, and they want to spread out as much as possible. And this says, and therefore tend to stay far away from each other. It does happen that they occasionally wind up on the same side of the atom. So remember, electrons are constantly buzzing around. And it is true that occasionally all of the electrons in an orbital will find themselves on one side of the molecule, making that side partially negative and the other side partially positive. We now have a dipole. Okay, now what's really cool about this, when that happens, let's see here. I don't want to get ahead of myself in slides. This says, at that instant then, the helium atom is polar, with an excess of electrons on the left side and a shortage on the right. So again, here is our partial negative, here is our partial positive. All right, now here's what's cool about this. Another helium nearby then would have a dipole induced in it. So when the first helium atom finds its electrons all on one side, it becomes negative on one side and positive on the other. What happens then is the heliums that are in close vicinity to this one particular helium actually get a dipole induced into them. Okay, we call it an induced dipole. This means that any helium atom nearby will align itself so that it attracts to this. So remember, in our first helium, this was the partially negative side. I wish this electron was like a little more, he should be a little more over here. Okay, that's where he lives. This is our partially negative side, so that means this is our partially positive side. And remember, this first one happened by happenstance, okay? These electrons just sort of ended up on the same side. Well, what that caused was any helium next to it automatically induced itself into a dipole, meaning its electrons ended up on this side because it is attracting to the positive side of this helium. Then this side is positive here, so this would attract another one, and so on, all around here. Okay, so this one helium atom that spontaneously aligned itself with a dipole has caused induced dipoles of helium atoms all around it. And while this is a dipole and an intermolecular force, it's not a very strong one. Okay, as you can imagine, dipoles that just sort of are happenstance and not permanent, and then also ones that are induced, it's there, it causes an intermolecular force, but it's just not very strong. So London dispersion forces are not, they are the weakest IMF. Okay. So like I just said, London dispersion forces are attractions between an instantaneous dipole. That's what we call the first helium, the one whose electrons just happen to end up on one side. We call that an instantaneous dipole. And the combination of that plus the dipoles that it induces around it. Okay, so the first helium atom was called an instantaneous dipole, and then the atoms around it are called induced dipoles. All right. Now, something that I need you to know, and we'll go over this a little bit more, LDFs, so London dispersion forces, are present in all molecules, polar or not. Even ones with hydrogen bonds, they're even present with an ion-dipole interaction. London dispersion forces are there all the time. However, they are not significant if a higher or stronger force is present. So while they're there, they kind of get overridden. So if there is a dipole-dipole interaction, that kind of overrides the London dispersion force. Still there, but doesn't really matter. Or if there's a hydrogen bond, that will override the London dispersion force. Again, still there, but not really having much of an effect on that liquid's properties or that solid's properties. Okay? Just a vocab word here, the tendency of an electron cloud to distort in the ways that we just talked about, this instantaneous dipole, is called polarizability. Remember, when we create a negative side and a positive side, we are creating poles, like the North Pole and the South Pole. Okay, so this is called polarizability, or we are making a polar part of a molecule. All right, now, one thing that I want you to know, and I would put a big star around this, this will be important. The strength of a dispersion force tends to increase with increased molecular weight. Okay, so what that means is, let's take a look actually at this table right here. All right, F2, Cl2, Br2, I2, these are all halogens, and they are starting from the top of the column 17, down to the bottom. Okay, what we notice is they get bigger as we go down. So the molar mass of F2 is 38, well, Cl2 is 71, and so on. Okay, so what we see as we go down a column is that we are increasing in molar mass or molecular weight. What we notice is that we get an increase in boiling point, which means, and I haven't discussed this yet, which means we get an increase in the strength of the London dispersion force or the intermolecular force. Okay, so the larger the element, meaning the more molecular weight it has, the greater the IMF. All right, this would be important. So, we could give you a question where we ask you to sort of rank the IMFs in amongst a set of molecules. And if there's multiple molecules that only have London dispersion forces, the way you would tell which one has stronger IMFs is to see which one has a greater molecular weight. The reason that this is the case is because larger atoms have larger electron clouds, which are easier to polarize. It's easier to have this instantaneous dipole that then leads to induced dipoles when you have a larger electron cloud. Okay, now I already did hydrogen bonding just so that I could kind of go in order of strength. But remember, London forces end up sort of near the bottom. They are not sort of near the bottom. They end up at the bottom. They are the weakest IMF. Okay, so let me skip this because we've already done hydrogen bonding. So here we go. Here is it sort of leveled out. So our strongest would be ion dipole, then hydrogen bonding, dipole, dipole, and finally London dispersion forces. Okay, so now how is this going to play out in terms of a question? We could ask, like what type of, sorry, that's my binder clicking. I'm trying to get out a worksheet so I can just get some Lewis dot structures for you. We could ask you, in this particular structure, what IMFs are present. So let's do something like that. Let's do, I'm just looking here. Let's do this one. So CF2SE. Guys, I just pulled this straight from a worksheet you've already done. But you can pause the video and draw this Lewis structure if you would like. Here is what it, why isn't my C working? Come on. There we go. Here's what it will look like, just quickly, roughly speaking. And then we've got some F's going here. I'll try to get into all my electrons for you. Okay, so first step, step one, always draw your Lewis dot structure. And you guys, honestly, in this unit, when in doubt, if you come across a question and you're just like, oh, I just don't even know where to go, draw a Lewis structure. Honestly, it is really the key to every question in this unit is to first have a Lewis structure. From the Lewis structure, we can tell so many things that we've talked about in this unit. We can talk about polarity, we can talk about bond angle, we can talk hybridization, we can talk electron geometry. Like there's just so many things we can tell. And now I'm going to teach you how to tell IMFs from a Lewis structure. Okay, so looking at this Lewis structure, I can see that this is a polar molecule. I hope you can see that too. On this carbon, which is the central atom, I have two different types of elements. If you have different elements around your central atom, you have a polar molecule. Okay, you don't have to think about it too much. If these are different, it's polar. Okay, another one you don't have to think about too much is if the central atom has lone pairs. For our purposes with our geometries, if the central atom has lone pairs, it's a polar molecule. Okay, so I know this is polar. I'm going to write that down. That's important. So then I think back to my my list of sort of IMFs. Okay, I know that this is not ion dipole because I don't have an ionic compound that has dissociated, right? Like NaCl breaking down. That's not what I have here. Okay, so that's a no. I know that this is not hydrogen bonding because I don't have hydrogen, first of all, bonded to O, N, or F. I have Fs, but not bonded to hydrogen. So this is not hydrogen bonding. However, it is dipole-dipole because there is a partially negative portion of this molecule and a partially positive portion of this molecule. If you're wondering how I did that, how did I know which end was partially negative, which end was partially positive? Remember, you can go back to your roots a little bit. You just take the electronegativity of fluorine, oops, where's my pencil? 4, minus carbon, which I don't know off the top of my head, actually. It might be 2.5. Ooh, don't quote me on that. But you would subtract them. Okay, and see the bond polarity here to know which part is more negative and which part is more positive. All right, so back to our list. I know this has dipole-dipole, so that is definitely sort of the reigning IMF that's controlling the properties of this molecule. But I also know that it has London dispersion forces, LDF, because every molecule does. All right, so no matter what, you should be putting this down. Now, remember, if it has dipole-dipole, those override the LDFs in terms of like what is controlling the properties of this molecule. However, they're still present. So if you're asked, hey, what type of IMFs are in this molecule? You're first going to draw the Lewis structure. Then you're going to determine it's polar. If it's polar and not hydrogen bonding and it's polar and not ion dipole, then it's just dipole-dipole, okay? And then you're also going to say IMFs because they're always present, just not always the force that's controlling things, okay? Let's do one more example. Let me change my pencil back. Okay, let's do this. Good old NH3. Okay, so let's kind of think about what we've got here. I'm going to erase everything. Whoops. Erase. Why does the eraser go away each time? I find that annoying. All right. Let's see what we've got. So I definitely know that this molecule is polar. There's lone pairs. If there's lone pairs on the central atom at this stage of learning, it is polar. Okay, so this is a polar molecule. Now, let's think about what we've got. Do we have an ion dipole force? No, we don't. This is not an ionic compound dissociating. Okay, do we have hydrogen bonding? Well, remember, hydrogen bonding is an H bonded to an O, an N, or an F. Yes, we do. We have hydrogen bonding. Okay, great. So I know this is going to be the leading force, or the force that is sort of dictating everything. However, I also have what comes after that. So it would be dipole-dipole as well, just present but not really controlling things. And of course, LDF. Okay, so the three intermolecular forces present in this molecule, hydrogen bonds, dipole-dipole, LDF, these guys, not so important in terms of its properties, but still present. This one controlling how this molecule behaves. All right, guys, let's just do one more. How about good old methane? So CH4, just draw this in quick. Okay, let's take a peek at what we have. So as I look at this molecule, it is certainly nonpolar, right? The bonds between C and H are polar bonds. However, they cancel out. There is symmetry to this molecule. Remember, if your central atom has symmetry around it, meaning all of the elements around the central atom are the same, this is a nonpolar molecule. Okay? Non-polar molecules, let's think about the IMFs. So is this ion dipole? No. Does it have hydrogen bonding? No. This is hydrogen bonded to carbon. That does not count. Is it dipole-dipole? No. This is non-polar. Okay, so then the only IMF this has is an LDF. That would be the only one you would write down. The others don't pertain. We don't meet the criteria. Wait a second. Why did I do that? Yes, check mark. Yay, this is what we have. There we go. That makes more sense. The only intermolecular force present here is LDF, and it is the one that is controlling the properties of this molecule. Okay? All right, guys. I hope that helps with intermolecular forces. I'll do another video. I don't want this one to get too long. So I'll do another video, a separate video on the properties of liquids and how IMFs control the properties of liquids. All right.